So what I'm going to talk about today is the kind of next generation of connected autonomous vehicles and how there's a new technology that can help basically keeping it safe, keeping it secure, and also not compromising the real-time side of things. What we're seeing is there's going to be this next, the next generation of connected autonomous vehicles are going to rely on really sophisticated microprocessors, domain controllers and vehicle computers. And with that comes a higher level of software content, software sophistication, okay? Often more like we see in the IT or the consumer world. And so what we're seeing is the desire to use sort of general purpose operating systems, but at the same time having the safety, security, and real-time behaviors, and really mixing that in with classic safety-critical AUTOSAR software. The problem is that once you start producing a lot of software on these more powerful processors, there's the potential for security threats to get in, especially when you connect the vehicle to the outside world, which is a necessity we saw from the BMW this morning. So what we've really been looking at bringing to the automotive world is the idea of secure virtual domains to run basically software of different levels of criticality on the same microprocessor. And in order to do that, you really need a strong separation foundation to basically ensure that there's freedom from interference between those different domains, okay? And so if you want to have an automotive virtualization platform, you can't just go and pick up a hypervisor that you'd use in IT. Because you really need to have separation and isolation. You need to have real-time deterministic behavior. Well, you try and use, VMware ESXi as a real-time hypervisor, it's not going to happen. Okay, but then this ability to run these different levels of criticality at the same time. So mixing AUTOSAR Classic or AUTOSAR Adaptive alongside an infotainment operating system. Kind of hard work. And then being able to control information flows between those. So isolating domains is really not much use if you can't actually communicate. And the communication is often the thing that basically breaks the security. So having the ability to control that information flow and control which domains can talk to which other domains and, basically maintain security throughout that is a really important characteristic that this technology has to have. So I'm going to give you a quick kernel comparison. So separation kernel's probably a new term to most of you. So this is your more traditional operating system. And what you can see is we've kind of drawn a line here of CPU privilege and non-CPU privilege, because that's the important thing. If a threat can get basically into this privileged part, they kind of get the keys to the kingdom. And so in a monolithic operating system, you kind of get into here, you can kind of do what you like, and you can take control of the microprocessor. So rooting Linux is a good example of that. You get in, you basically get root privilege in Linux, you can do what you like, okay? So we go, okay, we've got generation 2, microkernels. I'm sure most of you have heard of microkernels, and they probably seem like a really good idea because they've got this sort of least privilege idea where you take a lot of the services and you basically push them up into non-CPU privilege. The problem with the microkernel is this is still essentially an operating system. So regardless of where the privilege really has, you can still break in and basically do damage at the bottom here. So we come to the separation kernel, which is what we're going to talk about today, and that's different. So this has no operating system, okay? Everything is deprivileged. All this thing really does is basically program the hardware underneath to give these isolated virtual autonomous runtime environments that you run applications and operating systems in. The advantage of this is there's nothing to break into here. So if a threat comes in here, say this is the connected domain, it basically stays there. It can't see this domain. It can't get into here because everything is pushed up, including the virtualization. And this is a really key part to how you can keep something safe and secure while running on a single microprocessor. So part of the reason I'm here and part of the reason that we have a partnership with ETAS is we actually have an instantiation of this technology called LinkSecure. It's a separation kernel hypervisor. It's pretty much the only commercially available separation kernel hypervisor. Well, we did it the hard way. We built this from the ground up. We built this thing to be secure. And it essentially gives you the ability to map resources, to map and separate I/O, to offer real-time performance, because that's kind of what we do. Okay? We also give you the opportunity to do bare metal applications. So although it's a hypervisor, you don't have to run operating systems in these secure domains. You can run bits of code. And so as you're kind of architecting your system, you can have this mixture of general purpose operating systems, AUTOSAR, bare metal applications all running on this single processor. And they're all isolated from each other. So what we've been doing, ETAS, Scrypt, and Lynx, is really collaborating to use this technology as a foundational security technology to build a safe and secure automotive platform for this next generation of domain controllers and vehicle computers. Really helping to make sure that as more software comes in to do the AI needed for autonomous, that we can actually keep that safe and secure. It's designed to run on modern multi-core processors. It's also designed to run on processors that actually have hardware support for virtualization and memory management. So it won't run on every processor that is used out there. We're also now bringing the adaptive, or the AUTOSAR adaptive, alongside our POSIX operating system into this virtual world as well. Okay? What this really allows you to do is to preserve your legacy safety-critical systems while bringing them into a connected platform that's running other operating systems and other software stacks. You can't do that with a normal operating system. And what happens is you can securely partition your safety-critical from your non-safety-critical connected parts. So what we have here is a block diagram. So over here we have the CAN controller, kind of like the sacred part. And over here we have the outside world, i.e. the untrusted or scary part. And what we're really trying to show here is how you can take information from the CAN controller and pass it through to the untrusted part without having anything coming back. And what we do is we basically build shared memory channels which are unidirectional. They only go one way. We can put filters and guards in the middle to make sure that the information is the right information, and then we pass it to the domain that's connected to the outside world. If you try to do that with a traditional operating system, you're relying on Linux to do all of this separation and communication. It just simply doesn't do it. But because we enforce the strict separation, we enforce the directionality of communications between those separate domains, we can actually put something in place which essentially is a data diode. This can be used in automotive. This can be used in industrial, anything where you've got critical components, safety critical, trusted critical, that you want that information to somehow flow to the untrusted world. So going to the cloud, or in the case of automotive, you might want some messages to pop on the infotainment system that's also connected. So here's the biggest eye chart. So this is really looking at how we can combine a lot of different parts of a car as you consolidate into a microprocessor. So you're going to have different networks coming in from the car. You're going to have different applications dealing with the data that comes from those networks. You're going to have the ability to go to the instrument cluster. You want to communicate to the outside world. And what we do is we start building these secure domains, okay, and how the communication goes between them. Another cool thing we can actually do is we can encrypt communication as it flows here. So what we can do is we say, okay, I'm going to take information from here, it goes here, and I'm going to encrypt it before it goes anywhere else, especially out to the cloud. So it means not only are we protecting the stuff in the car, we're protecting the data as it flows out of the car, okay, and we can also protect the data when it comes in, when it's stored in the car. So for example, if you want to have over-the-air updates, well, we can have a domain to do that. It talks to the outside world. It's encrypted. They come in, they get stored. But they can also then say, OK, I'm going to take this, because it's hypervisor, I'm going to take this down for a bit, and I'm going to reboot this only. This is still going, this only with the new software. So we can actually do secure over-the-air updates with this technology as well, and have them encrypted at the same time. So in summary, we believe virtualization, or secure virtualization, is actually a key to introducing vehicle computers and domain controllers. It's sort of the future of how we're going to take all of this information in and out of the vehicles to enable autonomous, connected cars. We can bring different domains that have been traditionally running on single ECUs over to a powerful microprocessor system without compromising the real-time or the safety keys to it. And that's this separation, and separation kernel enforces that. We can combine the separation kernel with traditional AUTOSAR platforms. It's not replacing them. It's basically working with them and allowing them to be virtualized. And this is real. We're doing it today. We've got a demonstration, and it shows how this technology works. This is not new rocket science technology. We've been working on this for a long time, but it's actually really applicable now that the automotive world is starting to take these bigger multi-core virtualized, virtual-enabled microprocessors.
So my question is with regard to validation. So this part of the whole story is very fundamental to safety and security of future systems. So can you tell something about how you validate your software? Yes. So for example, how you ensure that you have this kind of data diode which you proposed? So just standard testing is probably not enough.
Yeah, so we have traditionally, this software has been traditionally used in avionics, critical safety avionics systems, but also in military defense systems. So there are a couple of different qualifications we have to do there. For safety, we've been through the whole DO 178C certification, which is for flight safety. For security, there's lots of different security evaluations that go on right now. Most of them are at a system level. The product was actually built to go through the highest level of common criteria security evaluation. What we're doing alongside ETAS is basically taking it through the 26262. And I think we're going to go up to ASIL D on that, because it is a critical. Because what it's doing is enforcing, foundationally the safety side of things. It has to go through that level of safety qualification or certification. The nice thing about this product is, because it's not an operating system, because it's not a hypervisor, certainly the bit that needs to be trusted, it's a very small, thin layer that all it really does is program the hardware to do the isolation, both of memory and resources. So it's actually a much easier product to take through a qualification, as long as the qualification authorities understand what a separation kernel does and why it exists. But honestly, having gone through this with the avionics and the defense world, they kind of get it. It's something we're used to doing. So the plan is, I think by middle to end of next year, we should have gone through a full 26262 ASIL D.
You presented the unikernel as an approach for a hypervisor, and then the benefits of the separation kernel in terms of safety, security, and real time. Can you say something also? Is there a performance hit for the increased separation, or what's the performance like?
That's a really good question. Thank you, Nigel. So if it was an operating system or a hypervisor, there would be performance issues. Absolutely. If you're relying on, for example, Linux and a Linux hypervisor, you'd have some performance hit, which would really compromise real-time and determinism. Because this product is neither, and is really just programming the hardware, it's not doing very much. Most of the time, it's basically told the processor, when it first boots up, this is how I want the memory to work, this is how I want the CPUs, this is how I want to schedule here, and then it kind of gets out of the way. So pretty much, there's not much software being run. The software is really programming the hardware. And once you've done that, the performance hit is minimal. I mean, we're way under 5%, depending on the processor and the functionality of the processor. But yeah, you can pretty much run your safety critical operating systems without any performance degradation. The other thing to note is that if you're bringing these safety critical systems from a microcontroller to a microprocessor, even if you're only getting one core, you're probably going to get some good performance up anyway. And so we don't degrade that, but we can help certainly make that performance right.
Meine Damen und Herren, willkommen zu diesem.
Ladies and gentlemen, welcome. This is going to be a topic which focuses on the application, and it will be completely different from what you heard this morning when we heard a lot about cars. We're going to talk about agricultural technology. I'm a representative of John Deere, but on the other hand, I work very much in the field of standardization, IF, AEF. So AEF is an association of agricultural engineering companies, and our starting point was how can we make sure that we interpret standards in the same way, because we have to combine implements from different manufacturers and they have to work together. So we were writing standards over a number of years, and in mechanical engineering what we said was, well, let's just put it there, then we will try whether it works, and if it works, it's fine. Now, when it comes to CAN buses, can you find out that you still have gaps? So we need to find out what to do, how can we close these gaps. That's why we formed this association, and we formed committees to work on these different examples. So we're not talking about security topics, we're talking about the communication between agricultural machines.
Sie haben es gehört, ich habe jahrelang im Traktorenwerk in Mannheim gearbeitet.
Now, I told you that I worked for the tractor factory in Mannheim. Now, the first thing is that we have a tractor. It's not worth a lot unless you take it to the church or you do your shopping. What you need is an implement, is equipment in order to, to make this a valuable equipment or valuable tractor. So a front loader like this. We also have weighing systems. We have positioning systems, so you can store positions for your front loader. And then we also have plow depth control. We also have all kinds of drives, dual clutch drives, everything you know from automotive as well. So all these are implements that that come with such a tractor. But the most important thing is that we have implements that come with some domain knowledge. So these implement manufacturers are the manufacturers that provide this knowledge. And as I said, all this could be done with a yellow, red, or whatever color of tractor. It's all about standardization.
ISO 11783, den ISO-Standard würden die nichts mit anfangen können. Das ist also ISO-Bus.
So that's ISO-Bus. It's it's like a name or a trademark, maybe not, but it's the label. Really, you buy a ISO-Bus capable implement, so you have a standardized interface, and these systems can work together. They communicate. All right. I brought along 2 examples, all in all 3 examples of automation. Now, one of this is liquid manure. Everybody knows liquid manure. All these evil farmers putting or applying excessive fertilizer onto the fields. And of course, our farms need liquid manure as fertilizer, but all liquid manures are different. So actually, what you want is you would want to be able to detect the nutrient content of your liquid manure as per a certain time, so that you know how much to apply. We have the near-infrared sensor. John Deere has got it in the market. We've had it in the market for quite a while. We can detect 5 different nutrients in the fertilizer, and the quantity to be applied, or actually the pressure, stays the same, but the fertilizer per area is measured by means of, or based on the ground speed.
So, also, wir haben den Sensor hinten im...
So we've implemented this sensor. You see these pipes here, 20 centimeters in diameter, so quite a quantity of liquid manure passing by. More slurry here. So you can see these different ingredients, and actually you then also see a map of what you've done. This is a web application. Based on the color, you can see how much hydrogen, in this case, nitrogen was applied to the field, so that I can do a nitrogen balance, a nitrogen account, so that you can always have proof of how much nitrogen you have applied.
Hier kommuniziert jeder Mähdrescher mit seinem Traktor.
So every combine communicates with the tractor, and the tractors also communicate amongst each other. They exchange these the lanes, as it were, so that they know where to drive next. Now this is a picture that comes from Iowa in the US. But of course, it works the same all over the world. So 2 examples. I've got a third one. Now let's now look into automation, tractor implement management. This is the communication standard that we're talking about. Now the tractor. Now the implement has got the domain knowledge. This implement knows what to do. But the tractor provides the energy, the tractor provides steering, ground speed, the 3-point hitch. So these are the different places where you can mount the implement. We've got hydraulic outputs, a number of them, up to 16 of them for each vehicle. Then we have power takeoffs. So this will provide the full energy of the engine to the implement. And we're now offering that the implement can have access to these outputs and control them.
Thema dabei, die Begriffe haben wir eben schon gehört. Safety, jeder Hersteller ist verantwortlich für seine.
Now safety, every manufacturer is responsible for the safety of their own product. Liability, I mean, as long as everything comes from a one-stop shop, such as yellow and green, then everybody knows. But what about a mixed system? Now we have a tractor manufacturer and an implement manufacturer. How can we bring all this together? And in our working group, we found, or we understood, that we need a possibility to make sure that only those systems that obey our rules, the standards that we wrote at AEF, we've got to make sure that only those work together. That's why we defined a security layer, a multi-brand or multi-manufacturer standard for this purpose.
Ja, und dann, wenn die Systeme zum ersten Mal zusammenkommen im Feld.
And once the 2 systems or several systems come together in the field, customers buy a new implement. So what they do is they check certificates, they exchange them via the canvas, they check whether they are signed, whether they have a signature, so they come from a trusted source. And if this is okay, we release TIM on both sides, and the 2 systems can cooperate. And in the end, we even exchange a secret key. I'm not going to cover that in detail, but the issue is that depending on the processor that you have in there, we've got 32 and even 16-bit processors. So this exchange of certificates may take up to 30, 40, 60 seconds. So let's assume you're on a road and you've got to wait, stand there, and you've got to wait 50 seconds. Then, of course, the motorcycle that comes will have collided with you already. So you need to exchange this secret key, and once we've done that correctly, then we can go back to work after just a few seconds.
Noch ein bisschen zu dem Security-Konzept selber.
Now, just a few words on the security concept itself. With Scrypt and ETK and other brands, we got together and formed a public key infrastructure, or we decided on a public key infrastructure, which we structured. I'm not going to talk about all those layers, but you can see that we have a level, a production level, but you can receive certificates before you already produce. You go to a field test so that you can do some testing. And we have your revocation lists. I don't think I have to cover them in detail here today. But of course, we need some kind of trust anchor. And we need an independent organization that awards certificates to the manufacturers. I told you about AEF and the conformance test, so that in a multi-brand way, we can determine whether these systems can trust each other or not. And we didn't want direct access to the PKI for individual manufacturers. That's why we decided that we take the existing database of AEF and we flange a PKI onto that, to which all the manufacturers have access. So all this is stored at AEF, and AEF will generate the different certificates for the OEMs.
Gut, wie sieht unsere Infrastruktur aus?
So what does this infrastructure look like? TIM software, which is part of your payload. We decided that the security software itself, all the algorithms, should be developed together. ETK was asked to do this as a partner, so they supply us with the software, which can be used by all manufacturers, because this is not a kind of, unique thing. We use it in common, or we share it, as it were. So the raw data go to the database. The developers generate the pair of keys, the private key that we don't see on the internet. The keys are transmitted. The public key goes to the database. The two are processed together. There's a signature, and the certificates are provided. You upload them to your software. So then you've got a software payload which goes to either the tractor or to your implement or equipment.
Wir haben also Multi-Brand Solutions, also mehrere Hersteller, die hier zusammenarbeiten.
So I told you we are multi-brand, several manufacturers working together. We want to make sure that you can trust each other in the field. Then safety and security, that's what we talked about, and the communication protocol, that we want a standardized protocol, that we've defined this for us as an industry. We have the AEF, which hosts the PKI for us. We share in the software development. We're now currently in the development phase, in the testing phase, and we will put first machines onto the field in spring 2018. And the aim is to be able to go live, start production at the end of 2018. And I've showed you several examples of wireless in-field communication, and we have a dedicated group working on that.
Ich finde, das war eine gute Vorlage von dem Herrn.
I think Mr. Nissen's presentation was very interesting because you see how it is all connected, and bus systems, that is also what I was concerned with when I came to Volkswagen. We are similar, but we're different. And we have reached a state in automotive electronics where the hacker issue and the vehicle in a cloud is. So it's very important, and I want to give you a bit of background what really concerns us, where the trends are going, and why we are looking into security and what we are doing about it to protect the vehicles and the data in the vehicles.
Das heißt, das Fahrzeug wird
meaning the vehicle will be always on in the future, as always on as we are in the smartphone industry. Here, more than 2 billion people are currently users of smartphones, and thus they're also on the internet. It'll grow. It is a huge trend. And now at 2015, there were 10% of the vehicles connected and were on the internet, and that will continue. And a forecast to 2020, about 25% of the vehicles will be connected to the internet. That's a huge hype with the e-cars. It made another jump because I want to see the charging status, where I want to pre-start, heat my vehicle while it's still on the charging pillar. I get the electricity from the charging station, and so if I heat it up previously, I can extend my range and all that.
So nehme ich mal so eine. Mir gefiel die Studie ganz gut.
I like this study, the bright future of connected cars, so that we know where we are going. An enormous increase of connected vehicles connected to the internet with functions from mobility traffic information. The information, is there a parking lot available? And sometimes you are really upset and you start looking for a parking place. And these are all services available now. And this is to bridge over to the security issue. I don't want to be directed to an area where there's no parking space available, but there may be some crooks who are waiting for me there. And in Simon First's video, there was a hazard warning. So if car 2X, that there is damage to the road or emergency functions, the remote operations, I already mentioned it. And what is interesting, also for us OEMs, also with the workshop you can and service, you can support your customer better. So if there is tire pressure problem or oil pressure problem, then you can direct the customer to the next service station, and that gives a greater loyalty of the customer to Volkswagen. Autopilot, we put it down twice here. Then Wi-Fi hotspot, that is also this VW hack spot we had. That is really a problem when we go over the hotspot. Over-the-air updates, how is it supposed to work for a vehicle? Because you can then by remote flash over the car. That is those are things that we have experienced, and providers, phone providers, are already more used to it, but it is also a major challenge for the OEMs. Then automatic adjustment, then driver detection, when that my settings as a driver are always stored, and also in the GPS system I have my last destinations stored, and so on. The mobility is changing. We have a test running with carpooling in Hanover, because people don't want to own a car anymore necessarily. We have to respond to that. People are working, and I cannot accept deliveries in my office, so I give authorization to the delivery service to put things into my car. The car has to be fast and dynamic. That is not important to the present generation. Features are more important. What kind of features, things that my phone can do, I want my car to do as well. Then a bouquet of connectivity issues. And very important here, everything that is put in the car has a potential security risk.
Die Vorlage war eben in dem Vortrag von Lynx letztendlich.
At the Lynx presentation, it was said the separation between the big, colorful online world and the world in the car, the trusted and the not trusted world, and the kernel, the separation kernel. That those are technologies that we have to integrate into a car. We are still in the world of the 16-bit processors, but I think especially with large processors, encrypted keys can be entered so that it doesn't take 50 seconds to check, which is another problem that we will have then identification and authentication methods. I assume that nobody can, as man in the middle, enter into the CAN communication. The separation is the key, and to identify attacks as well. Now, to be a bit more precise, now we talked about the motivation, but what are we actually doing? Practically all system installed in the car and connected to online functions, there is a process of risk analysis and testing. We test, as we know it from the safety world, an FMER. We are doing a risk FMER. What is the potential of happening in order to prevent it? And we take measures according. We have a vehicle key management based on theft protection. Just we are programming a key so that a key, only this key can open the car. And in the database, we have also the cryptographic keys, and then enter into the car functions like secure onboard communication, which adds to the complexity, but the shortcoming of the CAN bus that in the past, that somebody sends a wrong message to the CAN bus, that this can be prevented, that the signature is checked, as it were. So security has to be entered early on into the engineering process. Now, once we have started standardized production with all the measures taken, and we also implement an intrusion detection system, that anomalies are identified, and not only detected and identified, but what kind of anomalies, so that we switch off certain branches of functions in the case that there has been an intrusion, so we prevent any damage. And to find out before a hacker does, we have a penetration test in a normal testing procedure, as we are doing a standardized CAN test now, and quite normally we can do this penetration test in order to detect any weaknesses before anybody else does it. Now, what about the information we gather? It doesn't help you to know about a weak spot. You have to do something about it. And it's not only solved in the electronics department, but we sit down with the IT backend. So we talk about end-to-end backend to the vehicle through apps. So IT is involved, quality management, which is active in the normal fault detection. And we have formed a team to discuss what measures to take in such a case. Now, trying to prevent that this will occur, that an external source reports a hack, is that we have a database with the weak spots. If you take Linux systems, there especially in open source projects and with open source software, there are databases to the weaknesses of the system reported from other industries. So if I use this system, I might have a risk because of the weaknesses. Now, when we talk about AUTOSAR-based systems and we have a CAN bus driver from Bosch or Continental, then you don't find any sources on the internet to find out if a CAN bus driver from Bosch has a certain weakness as far as security is concerned. These are systems which we are right now testing if they help us, but we proactively can do something already before the hack is detected and with the EDS system. So we have a database with all the weaknesses, with all the software modules, and we are checking whether in the software modules there are any weaknesses can be corrected then, and then do a rollout in the cars to correct these weaknesses. And this doesn't stop with SOP, but continuously goes on, because there is, once the cars are in series production, SOP happens every day as far as security is concerned. And on the one hand, we have the Tier 1, on the other OEM, and what will be initiated over the next few years is to have a defined interface from our incident management team to the Tier 1s, to a Bosch, to a Continental, to Hella. Because if we have problems with weaknesses when we read something on the web, whom do we have to call? And at Bosch or Continental, you talk to one and they only have an insular knowledge, maybe. So it is important that there are certain central contacts. This must not necessarily be the experts, but the ones who, within the organization, hold contact to all the security experts. Because speed is of the essence here. If there is a hack, we cannot wait 6 months to find out who's the right contact at the tiers, because we need immediate support from the Tier 1s.
Vielleicht da noch mal ein kurzes Bild dazu.
And that is our car security incident process. We have formed a joint team with the implementation, verification, and reaction and response potential. And this, what drives us is not only the customer and the intention to improve our cars. There's a lot of new regulation which we have to take into account.
Connected cars.
Well, connected cars, a huge challenge as far as the security system's concerned. Hackers have now discovered cars as a potential as being of potential interest, and we have to make them more secure. We have still a lot of work on our plate.
Ja, vielen Dank für den Vortrag.
Thank you for the presentation. I think you outlined how security has to be implemented over the whole life cycle, but especially as far as the software updates are concerned. Have you any idea what the future business model should look like to finance them? Today we have an SOP and then the teams are dissolved, so who will make the updates? Well, it's not true that everything is over with the SOP. The teams will not be completely gone, but what is important is how do we reach the customer to allow updates in the car. And with the Windows 10 update, I think I spent the whole evening and the next day so that it worked. And that is something that we have to make easier. It is not the question of financing it or who cares for the customer, but how do we reach the millions of vehicles, and how does the customer make sure that the vehicles are online and that the software and the various model years, that they are compatible, because hardware and software status need to be compatible, and I think that is a huge challenge to find the right process.